Welcome back. In today's video, we want to simplify the following expressions into the form a plus j times b, which is rectangle form. The j is normally represented as I in complex algebra, but in engineering or electrical engineering, we use j instead of I because I represents our current. So let's get started with this video. So we first go ahead and let's take care of B, let's take care of A, but before that, let's list a few properties. So this one is Euler's identity, which is the complex exponential e to the j theta is equal to cosine theta plus j sine theta. Also, we have the power property. So the square root of j, that's the square root of 2, my bad. Square root of j is equal to j. So the half is equal to plus or minus e to the j pi over 4. Also, not a property, but we know that 1 over the square root of 2 is equal to square root of 2 over 2. So let's get started with A. So A is the positive square root of j plus the positive square root of negative j, which is equal to, and as we see earlier, that whenever we have a j to the power plus or minus, or if we take in the entire complex number to a power, we have to include our plus or minus. So we go ahead and do that. So that will be plus or minus e to the j pi over 4 plus or minus e to the minus j pi over 4. But if you did not want to, if you didn't use this property here, you would start by representing the positive square root of j as in a sense, not in a sense, but that would be e to the j pi divided by 2, and you take that to the half, and then you get pi over 4. Moving on, this in rectangle form is equal to square root over 2 plus j times the square root over 2 times the square root of 2 divided by 2. That's plus or minus. We have plus or minus square root of 2 divided by 2 minus j square root of 2 divided by 2. So you can write this. You can simplify this further, but basically we have this in rectangle form. So all we have to do now is use the combinations. So if we add, so if we use plus and plus, we end up with square root of 2 plus j times the square root of 2. If we go minus minus, we have negative positive square root of 2 minus j times the positive square root of 2. If we do minus plus or plus minus, we end up with 0 plus j of 0, which is equal to 0. So again, if we went ahead and apply Euler's identity for this portion, if we take cosine of pi over 4, we end up with the positive square root of 2 divided by 2 plus j, keep the j, and then sine of pi over 4 is positive square root of 2 divided by 2. Simplify that, we get both of these solutions. So we then go on to B. B, we have the positive square root of j times the positive square root of negative j. This is equal to, and still we go back and apply our power rule. And in this case, we can just skip to this step. But basically, we're not adding this time, we're multiplying. So we then go ahead and say plus or minus. You don't have to put this in parentheses. Well, you have to because you want to distribute the plus or the minus. So that would be positive square over 2 divided by 2. And then we have a plus. Oh, we got to keep our j. Remember our j. Positive square root over 2 divided by 2 times plus or minus, another parenthesis. Same thing, only time we change our j this time, because within the positive square root we have a minus j. So that changes to minus j. And that's what we have for that. This is already in rectangle form, so we can go ahead and multiply through. And we multiply a positive times a positive, and number won't change. And if we multiply negative through a negative, you know what happens. So basically this ends up at 0, a real number of 0, because after you distribute, so say for instance, we then go ahead and distribute. So if we times the positive square root of 2 divided by 2 times this guy right here, both of these cancel out to be 2. 2 over 2 gives 1, and so forth. And then after you distribute and combine like terms, you then simplify, and you'll end up with two solutions, which is a real part of 0, an imaginary part of j, and another one would be 0, an imaginary part of minus j. And that would be the solution for B. When we move on to C, C is then 1 plus j to the 2 and 1 minus j to the 2. So it's easier to multiply or divide in polar form. So we're already in rectangle form, but it would be a little bit more work to multiply that out and then divide. So we convert to polar form, and everything kind of goes easy after that. So division, and then we take the magnitude of this guy right here. So that would be the positive square root of 1 square plus 1 square, which will end up with square root of 2. And then we get a complex exponential, or we can use the angle, but let's just use the complex exponential. So this would be the inverse tangent to get the, so this would be, let's write that down. So it'd be EJ, and then to get the angle, we would go inverse tangent y, which is 1, and x is 1. So we would get an angle of pi over 4, and that would be in radian square. We get the same magnitude downstairs. However, though, for the minus j, our exponent in our complex exponential changes to a negative. So we then get negative pi over 4. And we divide out, it goes to 1. So that reduces to, and if we apply exponent properties, we know that will be, and we can just do that, that would be e to the j, pi over 4 minus a minus pi over 4 keep r square, and that goes pi over 4 plus pi over 4 is pi over 2. Pi over 2 times 2 is pi, so we then end up with e to the j times pi. And we then want to go back to polar form because we need the expression to be in the form of a plus j times b. So this guy right here, the magnitude of this guy is 1. So all you have to do is basically use Euler's identity, and cosine pi is negative 1. So we go ahead and write our cosine pi, negative 1. And then our sine pi is going to be 0. J times 0 is 0. We can just write it like that, which is ultimately equal to negative 1. And that's it for today's video. We will touch on a little bit of probably mixing sinusoidal signals and the complex algebra together before we go to the phasor domain. But I think in phasor domain, that's what we do. So I'll see you in the next video. Bye.